Hey, welcome back. In this video, I'm going to implement a finite state machine so that PsyDuck has some rudimentary AI to determine their behavior based off of the player's behavior. Let's get to it. So if you've never heard of a state machine before, this finite state machine rather is a number of states that are going to be connected to each other. Now, we've already actually done this twice in this video series. When we were using those animation controllers and we're going from one state, for instance idle, to another state, for instance walking, we're actually implementing a state machine. Similarly, we added some code to the animation for our Pokeball, all those different steps that we were traversing to somewhat have a little bit of a state machine as well. So that's what a finite state machine is, and the important part to remember here is that a game entity can only be in exactly one state at any given time. Otherwise, things get more complicated. So what does that look like for the game that we're making right now? Well, I think it's about time to talk a little bit more about the goals of the game. Because in this game, what we are doing is we're going to implement 10 PsyDucks, and the player gets to try to catch as many as possible within 5 minutes. Now, obviously, PsyDuck doesn't want to be caught, so we're going to add a state machine, or some AI, if you will, to make sure that PsyDuck has some interesting behavior for us. So first off, PsyDuck is going to chill. PsyDuck is just going to stand around and do nothing. However, when a certain amount of seconds have passed, PsyDuck will start to saunter, which means that PsyDuck is going to walk to a random destination on the map within the safe boundaries that we defined in the previous video. Once PsyDuck gets to that location, PsyDuck is going to start chilling again, and that's pretty much all PsyDuck does all day. However, when we get in PsyDuck's view and we're close, PsyDuck will flee and run away rapidly to a spot that is far away from us. And it doesn't matter if PsyDuck is chilling or if PsyDuck is sauntering. Whenever we are in view and we are close, we want PsyDuck to perform this behavior. So lovely. Now, how do we get away from the flee state again? Well, we can get away from PsyDuck, and when PsyDuck reaches their destination, PsyDuck will just go back to chill, and if enough seconds pass and we don't get in view again, PsyDuck will start to saunter again. However, if the player does not get away from PsyDuck, we kind of want to do something about it, because otherwise the player might just start to camp out and catch PsyDucks that way. So when the destination is reached, or if a certain amount of seconds have passed, we're dealing with a navigation pathfinding AI here, it might get stuck. So if a certain amount of seconds have passed or we get to the destination and the player is still too close, we're going to have PsyDuck dig or burrow or whatever you want to call it, and basically have them leave the map. And as the asterisk can tell you there, we are going to end the game if all the PsyDucks have left, or if the player has got them all, because you got to catch them all, right? So this is basically the simple state machine that we're going to implement now with just a little bit of code, and also an animation controller, because as you can tell, this already looks very similar to those animation controls that we have been implementing. So what I want you to do now is maybe just pause the video, because I'm not going to go through every step again. I'll just show you what the result is, and set up an idle that you can call chill for PsyDuck. Set up a walking animation for PsyDuck that will be your saunter. Set up a runaway animation where PsyDuck is running faster, and then have an animation for when PsyDuck will fall flat, is the one that I use from Mixamo, but we'll use that for the digging animation. And if you do all that, you should end up with the following. So the first thing that you probably are noticing right now is that this does not look as much as what I just showed you on the slide. The arrows are different, and that makes a lot of sense actually if you think of it. We don't necessarily, we don't need the animations to have the same state machine transitions as we would have for the logic. So what I've shown you earlier was mostly just looking at how does our logic work. It doesn't necessarily equate exactly to what the animation state machine would look like. But this is how I do it. So I set 3 booleans up. Well, first off, I create an animation controller and I hooked it up to the PsyDuck prefab. So this is not the PsyDuck in the level, this is the PsyDuck prefab, because otherwise the animations are not going to play for the PsyDucks that we're going to bring in. Okay, so then in the animation controller, 3 variables. There's no idle, but there is a saunter, flee, and dig. So why do we have no idle in there? Well, we just don't need it. The way it's set up is idle is whenever other stuff isn't going on, we are going to be in idle anyways. So it's not needed for our logic. What we do have though is we have a couple of arrows going in and out of idle, and then one that's just going straight out of idle. So since this all happens in the same frame, we can absolutely go from fast running to fall flat or from walking to fall flat, because if all the conditions line up, we won't stay in idle. We'll immediately go from this arrow to that arrow. So never think that there is going to be 2 steps in there just because there's 2 arrows, okay? So all these arrows, as you remember, have their exit times turned off, because otherwise the animation will play completely before it moves into the next stage. And we've put some very simple logic on there that we haven't even implemented in a script yet, because I think it's just so straightforward. So the first one is fast run. That's what we're going to be using for our fleeing. So when fast run becomes true, we flee. When fast run is not true, we are going back to our idle and let the animation controller take it over from there. Same for walking. When Saunter becomes true, we're going in. When Saunter becomes false, that's what I clicked on right now, we're going back out. And then finally for dig, whenever it comes true, we go in there. If dig happens to be false, we honestly don't care, because as soon as the dig animation is going to start playing, PsyDuck is going to leave the stage and we're going to make him disappear anyways. So this is our animation state that we have. The other thing that we need to mention is we want these to loop. So on all of these animations, with the exception of fall flat, which is unchecked, they're going to be checked because we want the loops to be enabled. And that is all the animations we have to do for PsyDuck. Nothing too spectacular. It's actually less complicated than what we were using for our player controller here. So all right, with that in place, we can add some code to make PsyDuck have a little bit of a mind of his own. All right, so this is what we had from our previous video, and we can just delete everything except the game object trainer, because we probably want to still have something going on with the trainer. And with that in mind, we can start declaring that variable. So private game object trainer, and we can just leave it empty so that it can be used later on down the road here. All right, very cool. Another thing that I want to set up already as well is, because looking at our state machine, we are going to use a random, and rather than going through this thing when we actually get there, I'd rather just set it up directly here myself. So we want to use the random that comes with Unity Engine. So that looks like so. And we're not using it yet, but once we use it, we are going to be using the right random out of those 3. That's the one I like to use for this type of stuff. All right. So what other kind of variables do we want to declare? Well, first off, I kind of want to set up that state machine in a very bare bones fashion. So to do that, this time around, we're not going to work with regular variables. We're actually going to create an enumerator, which is pretty much a variable that can hold a number of constants. And in this case, our constants are going to be chill, Saunter, flee, and dig. So similar to, I don't know, where have we used an enumerator in Unity earlier? Oh yeah, I remember when we used lock mode for the mouse. So don't copy this code. I'm just writing this to demonstrate. But if we do, let's see, cursor mode equals to cursor lock mode, we get these options: confined, locked, none. So these are 3 options that are associated with the enumerator cursor lock node. In the same way that we're now going to have a private enumerator called state that will have state.chill, state.saunter, flee, dig, and we can use that to figure out where we are at. So let's set up a couple of private variables to keep track of all this type of stuff. So the first one that I want to use is private state. Well, actually, so it's going to be a state enumerator called current state. And actually, we can serialize that one. Because if it's serialized, we can easily see it in case we need to do some debugging from the editor. So that is going to be helpful. And then I'm going to set up a private Boolean called transition active. Make sure I don't get any typos in there. I'm going to put those close together. I don't think that's going to lead to issues. Because what I want to do is I want to have I want to check that Boolean in the beginning and run some code there at the very beginning the first time we are going into a state. And by switching transition active to true or false, we can do that pretty easily. So anyways, let's get to our update method and add a switch. And this switch is going to check our current state that we are in. Okay? So switch current state, and then we do that. And our state can be a number of cases. So it could be chill, Actually, like so. Break. It could be, well, all the other ones. There we go. Well, I'm not going to fast forward this one just in case you are typing along with me. Break and case state Saunter break. Now, I don't like the order that these came out in, so I would like flee. There, I would like them in this order. That makes more sense to me. I like it better that way. So, yeah, when we go into update every frame, we're going to check what the state of our Pokemon is. If it's chill, run code in chill. If it's Saunter, run code in there. And what we're also going to do is we are going to look for the first, when we get into a transition. So we're going to check if transition is active still. And if transition is active, we are going to, for now, set it to false. All right. So I'm going to add that everywhere. So this is basically our arrow coming in, and we can just run some code here as we go into a state that then immediately we become disabled. The only thing we have to do is whenever we switch states, we need to set transition to active to run this code first. So keeping that in mind, the next thing I want to do is create a couple of methods to make sure that every time we switch a state, we are setting that transition to active so that we can actually add some code in here that is going to run with us. So let's set up a couple of those methods now. Or actually, we can probably just do it with one method because we can just feed the state into the method and work with it that way. So let's have a method called void switch to state. Oh, actually, this is right. Yeah, so this is going to lead to errors. We need to put the method here so it's not part of the update method. So switch to state, and we want to accept a variable, a state variable, and we can call that one, what would be a good name, like new state or something like that would be good. And what we want to do is, first off, we want to set the transition active to true, so that whenever we're using our little state machine here, we're going to come in and we're going to run whatever code we put in here once and no more. And that's important because, for instance, the code for, as I showed you in the previous video, the code for setting the destination so that PsyDuck is going to run somewhere else, that can only be ran once. So it's super important to have this, you know, it's like pretty much like the start method for the entire class. Sometimes you want to just run code once, so that's why we're doing that. And then we're going to do current state equals to new state. So whenever we run this method now, switch state, we are going to set the state to whatever we are putting it into. And I think to start the game, what we want to do is we want to switch state, and it's going to be state.chill. What did I do wrong there? Switch to state. Let's see, state. Oh, capital, of course. State.chill, and that should do that. Okay, so with that we have the rudimentary skeleton for our state machine ready, but you know, there's nothing really that I can test right now that would be easy to see. So let's put some code in to make PsyDuck go to a different location, perhaps. Maybe that would be a good thing to do at this point. So let's do that. So let's set the current destination for PsyDuck to something. And well, to set the current destination, I'm going to have to create a variable for that. So let's start with that. So let's create a variable, private vectors3 current destination, which is a variable that we should probably serialize as well, because if we run into any issues, it's going to be easy to debug and see. Plus, we can also just change it manually at that point, maybe, in case we want to send PsyDuck to a specific spot for debugging purposes. Also, while we're at it, we might as well create another field, because we're going to mess about with the run speed of PsyDuck a lot. So let's make one called run speed, but that's not going to be a vector3. That should just be float. All right. And let's see what other kind of things were we going to be using. We were going to work with a view angle. Well, we want to check if the player is going to be in view at some point so that we can flee. So let's set up a variable for that as well. And let's say, well, we are going to use a dot product for that. Spoilers alert. So we're going to have a view angle variable, a variable that we can use to detect the view angle of, if you remember that video, between -1 and 1. So we can have a view angle if we're between 0.75 and 1. We know that the player is in range. So let's do 0.25 as a view angle, which we are going to subtract later on. And we could make this a serialized field as well so we can edit it. But for testing purposes, I think it's neat to just keep the code there, because that way I can't change it inadvertently. And then the distance from which PsyDuck feels safe from us. 0. Oh wait, that's ridiculous. Let's do 5 feet. 0, like half a meter. Like then we're already way too close. Like 5 feet. So we're going to use these variables for the part where PsyDuck is going to flee from us or not. What else do we need? We need to grab a hold of our animator. So let's do private animator, and let's call it Pokemon animator, because if we call it animator, we're going to hide the animator variable that's built in, and we don't want to do that. So that's one thing we can do as well. And then, well, we set our, I think I set a run speed here. I think what we want to do is we want to also have a walk speed. So walk speed or walking speed rather, let's do that. Yeah. So now I got, okay. I think this is a good starting point for stuff that I'm going to need in terms of declaring variables. So we have our enumerator, we have our current state, and our transition active, which is all state machine stuff. We're going to keep track of our destination with current destination. We're going to have some stuff to determine the walking speed, some stuff to figure out when we are looking at PsyDuck, or rather PsyDuck is seeing us or not. And then we're going to mess with our animator, and we're going to mess with our trainer. So that's a whole bunch of variables. Time to put some wheels in motion here and get everything going. Although maybe, we might declare some stuff up here as well. For instance, the walking speed, the starting walking speed, it might be a good idea to just go with whatever the default speed is that we're getting from the editor, because, oh shoot, I messed up here. I need the nav mesh, get component here. I need the nav mesh agent component. So this is the component that we added in the editor. I want that one, and that one has a whole bunch of, this is going to throw up an error probably, but if we look at our PsyDuck, we already have a speed here. So this is the speed that I want to grab through the code. So let's go back to my code and just grab that speed, and in the start method, we're going to set that at the beginning of the game. So whatever we put in there is going to be our speed. So it's going to be 3.5, which is probably way too fast, but that is fine for now. And our Pokemon animator, instead of, because usually what I've been doing in the past, just to show you how you can easily make connections and keep things pretty easy, we're going to actually grab it now through code instead. Because you can just as well, with the get component, you can also just grab an animator, just grab it this way. And yeah, so this will have us connect to everything we need here. Like I said earlier, what I have done in the past is create a variable and drag that in here. We're at level 2 now. We're just going to do this type of stuff with code, because there's no point. I want to be able to just drag and drop PsyDucks in there without having to hook up a whole bunch of numbers and values and all that kind of stuff. Actually, with that in mind, it might not be a bad idea. Let's do that as well. To go into our prefab, go to PsyDuck, and immediately maybe, that's really good that I did that, because apparently I forgot to hook up the nav mesh agent. That's a big mistake. That's going to lead to a lot of errors. So yeah, make sure that your prefab has a nav mesh agent. And then I'm going to set the speed to 1 here, which is that's a good Saunter speed in my opinion. Let's do that. And everything else we can just leave by default. No, this needs to be 0. And this needs to be 0.8. The radius and the height, like we did for everyone. So if we do that, we can actually, how about we just delete this one here to make sure we get rid of him, and then just bring in a new PsyDuck, and that PsyDuck will have all the stuff connected to controller and everything. All right, so with that, we are ready to, we have everything. We're ready to start filling out this state machine and get everything going. So I think first things first, maybe let's have PsyDuck go from chill to Saunter. What would that look like? Well, if we're looking at the slide, we are gonna wait until a certain amount of seconds have passed to go to Saunter, and then in Saunter, once we've reached the destination, we're going back to chill. So that's the part we're gonna focus on right now, just this. So yeah, let's see how that works. So seconds have passed. Whenever we're thinking about delays and timing in Unity, we wanna start thinking about coroutines. But in this case, I'm actually going to use the invoke method, which is kind of an easier way to do a coroutine. So last video in which we needed a delay, we used the coroutine. This time we'll use the invoke method. Then we're going to have to create a method to figure out what a good destination would be to Saunter to. Then all we have to do is store that somewhere, see when we reach it, and then we go back to chill. So easy peasy, right? Let's go do it. All right, so maybe let's just start with that method. And I would like to call this method ValidDestination. It's going to output, or it's going to return a vector3. So vector3 ValidDestination. And what are we going to do here? Well, we are going to create an array. Now, I'm going to provide some extra information on what arrays actually do, but we're going to create an array, a list, if you will. It's not actually a list, but just a succession of numbers, or floats rather. And we're going to call that array boundaries, and this is how we're going to declare it. It actually uses the curly brackets as well, and it's going to be a multi-dimensional array, and we're going to put the following values in it. So 0, 140, then -60, and 40. Now, if you're thinking, geez, I've seen these before, you would be correct. Those are the coordinates on the x-axis from the lowest point and the highest point that we put those Pokémons for the safe spots, and then on the z-axis for the lowest and the highest points as well. So within this, we're basically creating a square, a safe boundary in which we're gonna calculate destinations that fit within these spots. So that's what I would like to do. And we also know that if we want to send our Pokemon to, I don't know, 0, -60, that's one of the easily locatable, fleeable safe spots that we declared when we were designing the map in the previous video. All right, so let's make some local variables here. So float x is going to be equal to random range. We've already implemented random, so we don't have to choose. And it's going to be boundaries, and this is how we can find the numbers from the array again. So 0, 0. So that means the first number, because 0 is actually the first number from the first group that's in the array. So that will be 0f is at 0, 0. So at 0, 1, we find 140f. At 1, 0, we find -60f. And at 1, 1, you guessed it, 40f, right? So 0, 0 is going to be the lower range for our random number. So it's going to be a number between 0, 0 or alternatively 0f and 0, 1, which is 140f. Okay, so that is going to be the value that we're going to calculate for our x, and for our z we're going to do the same thing, but we're going to do 1, 0 and 1, 1. So this is just to grab these numbers, because we're going to be reusing these numbers a lot. So we're basically writing random range 0f, 140f, random range -60f, 40f. Okay, I hope that makes sense. Now keep in mind though, if you don't have exactly the same terrain as I do, which you won't, these numbers are going to be different. You need to figure out yourself where those Pokemon actually have safe spots on your map and what is going to be the playing area for your map. So don't just copy these exact numbers, because they won't work. You need to find those 4 spots like we did in the video and then put those values in. All right, cool. With that out of the way, our destination. So again, local variable to this method is going to be a new vector 3, actually. And the new vector 3 that we're making is gonna use x, y, and z. Easy. However, y is gonna turn red because we've declared an x and a z here using the random range. This is actually a 2-dimensional thing, but we still need to figure out what our y value is gonna be. So we're gonna use some code that Unity has, because Unity has a terrain class that we use to create the terrain. And we're going to select the active terrain from the terrain class, which is the terrain that we have in our map. And we're going to sample the height at a specific spot. And if you're guessing that that spot would be the x and the z that we are using, you would be correct. So the position that we want to sample at what the height of the terrain would be in terms of world coordinates, well, that would be, we need to get a new vector for that as well. So let's do new vector 3. And I'm really going off screen here right now. Let me clean this up a little bit so it's easier to see for you guys. So, new vector 3. So at x, whatever we put in Y doesn't really matter. And then Z, okay? And that should do it correctly. So what we're writing here in code is we're getting a destination, which is going to get a random number between 0 and 140, because we calculate that here. Then we're going to get a random number for the Z coordinate, which we calculated here between minus 60 and 40F. So that's our safe zone. And then we're going to look at the active terrain, and we're going to see what the Y value is going to be at that X and that Z, which can be whatever. Like, it's, you know, depending on how high the terrain is in that specific spot. So that our destination is literally a spot on that terrain in 3D. And once we have that, we can just return the destination. There we go. And then everything will turn green except this here, because we're not using that yet. But that's a neat little function. So we're going to have to try it out and see if it works now. So let's get up here and let's go to our Saunter and let's set the destination here. All right, so our destination can be, well, we're using current destination for this anyways. So current destination is going to be equal to a valid destination. And yeah, that's pretty much going to be it. There we go. Now, that's not going to do in itself. Now, we actually don't need this variable. If we, you know, we could just literally write the following. Nav-mesh, grab the nav-mesh, here the nav-mesh agent. So this is our Pokemon. And set the destination to valid destination. However, if we do it this way, it's easier to just track it because it's going to be part of the object in our editor as well, because destination is not something that the nav-mesh engine has serialized. So that's why I like to do it like this. So it's easier to see where our Pokemon is heading. Now, the important thing though is what you do not want to do is put this line of code at the bottom here. Because if you put it at the bottom there, it's going to run every frame, which means that the calculation for the nav mesh is going to happen every frame, which will probably still run fine on your computer, but it's not a very optimal thing to do. So by putting it here, as soon as we go to Saunter, the pathfinding will calculate how to get to the destination, and PsyDuck will just go there, and it should work out. Like, if we find that PsyDuck gets stuck too often, we can make, you know, we can add some code to make him do this again. But for now, this should work absolutely fine. And yeah, so that should work. Now, however, the only issue is we're going to start in chill, and there is no way from chill to Saunter. So let's add a little bit of code for that. Now, when we are going into chill, no matter what our destination or current destination is, we want to set it to the position. I made a typo. There we go. To the position of the Pokemon. We don't want, when we're chilling, we're staying put. So we can do that. And we can also add the same line of code to that so that PsyDuck isn't going anywhere. That's fine. However, how do we go to Saunter? Well, there was going to be a delay to do that. So instead of writing a coroutine, this time we are going to write an invoke. And invoke, let me open that up real quick. Oops. There we go. External documentation. So invoke will take a method and a float. So kind of it's like shorthand for a coroutine. So it will run this method and then in a certain amount of seconds. Now, the issue with that though is that method, as far as I'm aware in my testing, is just a string that is the name of that method. So it's not gonna accept any arguments, which can be a bit of an issue because we need an argument to get to a certain state here. So we're going to have to be a little bit more creative than that. So instead of doing our switch to state like this, and then do the state.saunter, as you can see, that's not going to work because it's just a string. So what we're going to do instead is we're going to make another method called switch to saunter, and we are going to run that on a random time. So let's do random range again. And the time call, we can set it to whatever we want. Like, how about 5 and 6 seconds for now. And actually, I didn't think about that when I was writing my code here. So maybe, well, we can serialize it at a later time. Let's just do 5 seconds for now, and it's really easy to mess with it. But we still need to create this method because this method doesn't exist. So what we'll do is we'll make another method, void switch to Saunter, which doesn't take any arguments. And it will do, unfortunately, well, actually, we don't have to do this. We can just do switch to state, there we go. And then we can just feed it. And it's, yeah, it's a little silly to do this, but that's just how we do it for this. So if we want to go to Saunter, we can do it that way. All right. So this would make it so that we are going from here to there. Now, while I'm at it, might as well just do an update to the Pokemon animator, right? Now, to do that, though, I kind of want to add a method as well, because I don't want to just start writing all these booleans and update them every single time, because that would just get really, really cumbersome. So what I would like to do instead is just write a method that's going to update that for me. So how about we put it down here? That looks like a good spot. So void update animator, or rather, let's call it Pokemon animator, because this is specifically for Pokemon, right? And we are going to take a bool, and we're going to call it Saunter. We're going to take another bool, and we're going to call it flee, and we're going to take another bool, and we're going to call it dig. And these are the booleans that correspond to what we have in here, because we're going to set these using this one method and make our lives a lot clearer rather than easier necessarily. So Pokemon animator is the variable that we are using, and we're going to, similarly to what we did for our player, we're going to set the bool in that animator controller, and the name of the bool is going to be Saunter first, and we're going to set that to Saunter. So if Saunter becomes true, oh, what did I do? I don't know why my brain went there, but yeah. So if Saunter becomes true, Saunter will be set to true. If Saunter becomes false, Saunter will be set to false. And we can do that for the other ones as well. Let's do the fleas. Let's do the digs. And we didn't have an idle. So now we have a cute little utility method that we can use to keep things a little bit nicer, a little bit cleaner. And we can just add the code up here to do that kind of stuff after our invoke. So let's do update Pokemon animator. And in this case, we want to go to Saunter. So no, actually, when we are in when we are in the chill one, we just want them all to be false. So we can just do it like that, which is great. But when we are going to do the switching thing, we want to make some changes to it. But like this will put us in chill, and that looks good to me. Right. So when we get the Saunter, however, we want to do the update as well. And now Saunter becomes true, and all the other ones become false. And what I really like about, I mean, I'm sure you can see this as well, you know, Writer will literally tell you flee is false, dig is false. Like usually in your code, if you're not using Writer, you're probably not seeing these things. And they're so, so helpful to not make any mistakes. But anyways, I think that should do it. After 5 seconds, we go into Saunter, we're going to get a location, and hopefully everything goes well. Let's fast forward and see if any of this stuff is working. All right, so it looks like we have some issues in our code. Okay, string bool, but at the same time, everything kind of seems to be working. So there's a parameter that does not exist, but we waited for 5 seconds and PsyDuck started walking. And as you can see, PsyDuck is going to a certain spot on the map. And we can see here at the current destination is this here. I have no idea where that is, though. It could be super far away. It could be close by. But since there's no way to go back, I don't think there's any point to waiting and following. But I do want to resolve this thing here because that's looking a little bit silly right now. So let's see what's going on with that. And of course, it's just a silly typo there because the variables that we are using in our state machines here are capitalized. These need to be capitalized as well. And funny enough, it never really impacted our execution of the code. So that's good, and this should make that warning go away. I'm not even going to check at this point. So yeah, that's great. So how do we go from Saunter back to our chill? So okay, well, what we can do here is let's write some code to look at if transform position. So if our Pokemon's position minus the position of current destination. Actually, I think we're going to have to encapsulate it one more. If the magnitude of that, so the length of the vector, so that basically gives you an idea of the distance between these two vector points, right? So if that is less than, let's say, 2.5, I don't know. If the point is going to be maybe like in the middle of a tree or something, I kind of don't want to have PsyDuck try to run around that tree trying to get to the point. So 2.5 meters should do it. I don't think we have any colliders that are bigger than that. So if we get that close to the point, we're there. We're basically there, right? So then we're going to switch state back to chill. Here we go. And otherwise, or actually, I don't think we even need to do an otherwise. That should work just fine. So yeah, when that happens, PsyDuck should go back to chill. And I don't know if it's really worth the time right now to already try this out. But feel free to have a look if this works. It should absolutely be working. But with that in mind, let's go back to the state machine and see where that brings us. So we've implemented the chill and the Saunter now, and I tested it off screen. Everything was working pretty well for me. You could even go from chill to Saunter to chill to Saunter back and forth because, well, we have the state machine working now, even if it's only 2 states. So the next step, when the player is in view and the player is close, we want to flee, and we want to do that from both of them. So let's make that happen starting with when player is in view. Now, ask yourself, how can I figure out if the player is in view or not? And if your answer to that is it's a dot product, then you've been paying attention. So this is what we are going to be implementing. We're going to use the vectors3 dot function that comes with Unity, and to figure out if something is in view or not, or actually to calculate a dot product, really, we want 2 vectors. And the vectors we're going to be using are the ones that I put on the slide. So first off, we want to know the vector between our PsyDuck and our trainer. And to do that, we can get trainer.transform.forward minus transform.position, which I've already explained. You need to subtract them because then you'll get to the center of the circle. Because if PsyDuck is somewhere up here and the trainer is up there and you want to move it to the center of the circle, you want to do the subtraction. Anyways, so that is how we can get this line, this angle. The second one that we want for the dot product to be calculated with Unity is we want to have our forward vector, really. So just transform forward. All of these need to be in world coordinates, so these will do it. And then the final thing is, if we want to have a readout that's going to be 1 for straight ahead and -1 to be behind, or 0 for left and right, both of them need to be unit vectors. So to do that, we need to normalize the one on the top here. So let's put that all into actual code. All right, so let's start with creating a function or a method that I'm going to call inView, and that method is going to take a game object. The game object is going to be our target. We're going to take in a float, which is going to be called viewing angle. We already declared one called view angle, but I am going to just make one called view wing angle, so we're not mucking up the variables that we already have, even if we're going to use it as a parameter anyways. So then we can do a local variable called dot product, and we're going to use that vector3 class function or method called dot, and it's going to take the left-hand side and the right-hand side. So the first one, as I mentioned earlier, is going to be our forward vector. The second one is going to be the normalized version, because we want our result to be between -1 and 1 of our target transform position minus transform position of PsyDuck. And with that, we calculated our dot product, which is going to be between -1 and 1. Feel free to experiment a little bit with it if you like in your own code. So if we then do if we just do 1, which would be straight ahead of us, and we subtract that viewing angle, which, viewing angle, which is going to be 0.25. If we're between 0.75, we know that we're kind of in view. I think that's a good viewing angle. That's a commonly used one in video games, so let's use that one. And don't forget the F here, because if you don't put the F in there, it's going to turn to an integer and nothing is going to work. So don't forget the F there. And then the distance, we also want that. Well, to calculate the distance between 2 objects, you just subtract the vectors. So we've already done that a ton of times. Actually, it needs to be this one here. There we go. And then get the magnitude. All right, so that is going to be our distance. And then finally, the check. If the dot product is larger or equal to our view, then we know that we are in view, but we also want to check that the distance is close enough. So our distance also needs to be smaller than our viewing distance that we're going to input at the top. If that's the case, we return true. And if that's not the case, we don't need to put an else there. We can just do return false instead. There we go. All right, that's some neat looking code. But yeah, that all looks like it should be working. And again, don't forget to put the F here. If you're kind of new to Unity, that's easy to forget. Because then it's an integer and your viewing angle, this will become a literal, turn into an integer. So, all right, cool. So then we can go up here, I guess. And let's add some code for that. So if we are in view, so in view takes the game object trainer, then the view angle that we declared already at the top, and the view distance, which we already declared as well. So if that is the case, and this turns true, we want to switch state to state.flee. All right. And I capitalized it, so I have to make sure that I capitalize it here as well. And that will take us to flee. And I think the same code should probably... I should not put this in because this needs to run every frame. So we don't want to put it in the transition active check. We want to put it below here because this needs to run every frame. Every frame we want to check that the trainer is not in view. And we want to copy that code over to our Saunter as well. So down here, make sure you don't put it in the wrong spot either. So yeah, so if we're in view here, that would put us into our flee state as well. And we probably want to go check that real quick. So let's just write log. Yeah, let's just call this flee. All right, let's go check it out. Oh, and that gives us a bit of an error. We get a null reference exception. So that means that somewhere an object is not getting a target. So if we, how do I debug this? Because this is actually a good way of doing it. So I double click it and I tried it. Well, I pause first and then I double click it and I inadvertently clicked again. So let's do this. And it'll take us to in view. So that means something's going wrong in the in view. And strangely enough, Rider is not picking this one up. So Rider is kind of missing it. So this is actually a really difficult one to debug, I guess, because Rider's not picking up on it. But it's telling me an object reference is not set to an instance in the thing here with with the in-view function that we have. And it's talking about, it's not really declaring which one it is. So, it can be viewing angle, viewing distance, and target. So the first thing I want to do when this happens is just have a quick check in view. Yeah, these all look green, so that should be fine. These all look green as well. So let's see, how did they get declared? Viewing angle, view distance. This gets declared here. Found it. So this is great. So that means, so what's going on here? We're creating this game object trainer, right? And this is private. But whenever we put that in here, we are redeclaring it again. So that's causing the issue probably. So if we get rid of the game object part so that we're not redeclaring it again as another variable, I guess, this might do it. So let's try this again and see if that solves the bug. And yep, that did solve the bug. Okay. So that's unfortunate, but yeah, it's not something I can go back and fix. So look at our little sauntering PsyDuck. Let's see what happens if we get in its sight. Flee. Okay. So yeah, that looks like it triggered, and it triggered from Saunter at this point. So let's see what happens if because we can see the current state up here actually, because we serialized it, which is super convenient. Let's go back again, and let's try to get in there while the chill is still going on. And as you can see, it immediately went to flee the state. So that's lovely. All right, Excellent. I'm not going to worry about that warning just yet. We'll deal with that later because there's still some stuff here that is just not great yet. So let's add some code and define what it actually means to flee. So the first thing that you want to do here is check how you got to flee. And in this case, we are doing an invoke, basically calling a coroutine. So we want to make sure that that gets canceled, because if we are in flee, if we get to the flee state from Saunter, which could totally happen from this here, this could still have been invoked. Well, actually, no, because we've already switched to Saunter. Well, anyways, just to make sure I don't run into any issues with that, I'm going to cancel an invoke here. If for some reason switch to Saunter is still ongoing at this point in time, we cancel it. And it's just a fail-safe. We might not actually need it. We might need it. I don't know. But yeah, just to make sure, I'm just going to put it in there. And if we're sauntering, our current destination is going to have to change. So we need a new valid destination. However, at this point, just a random valid destination like this stuff, that's not going to work. We want to make sure that we get one that's going to allow us to avoid the trainer. So what I want to do here is I want to set up some additional code that if we add a boolean that has us avoid the trainer, will send us to one of the extremities, those safe zones that we put together in the previous video. So how do we do that? Well, pretty simple, really. So if our trainer position, so let me just finish all this stuff here. Position, if the x value of that minus the first value of our boundaries, 0, 0, is smaller than or equal to, but that doesn't really matter that much, the boundaries of, oh, actually I shouldn't close it yet because we're still working on it here. Boundaries 0, 1, so the largest one, minus the position of the trainer, position x, there we go. If that is the case, that means that we want the x on our destination to be equal to the lowest of the two values. So boundaries, oh, whoops, like so. While if that is not the case, we want to send, PsyDuck, I almost said Pikachu, to the other one of them. So basically what this code is going to run is, we're going to look at if our player position minus the boundaries, if that value is smaller than the other value, we know that our player is going to be closer to the other value than this one. So we just want to send them to whatever is further away from the player and vice versa. So that's basically what this does. It's just a pretty straightforward way to see, okay, how does our player positioned in relation to these two values? And whatever he's the closest to, we go to the other one. All right. So then we just do this again. And we're just going to copy this. So, but this time we're going to change the z. So let's change the z first. I mean, I could have just done a replace function, but whatever, it's not worth it. And instead of these now, we're gonna change the first to 1 because we want to get the z values from our boundaries up here. We want minus 60 and 40 in this area, and we want 0 and 140 in the top area. So this will send our Pokemon on its way when we're avoiding the trainer to literally go to one of those spots. Because if we, like for instance, if everything aligns, we might send the trainer to boundary 0, 0, 1, 0. So that would mean to 0f minus 60, which is literally one of those safe zones that we declared in the previous video. So with this logic, we can make all of that happen, and that will send us to a safe destination. Now, we are getting some errors though, because valid destination only has 1 parameter, and we're invoking it with 0 parameters. So where are we invoking valid destination again? Up here. So in this case, when we are sauntering, that's fine. We don't need to avoid the trainer. It can just be false. However, when we are going to flee, we do want to avoid the trainer and we want this thing to be true. So that's one thing that we want to do when we are fleeing versus when we are sauntering. We want to make sure that instead of just going to another random destination, we could literally be right next to the player. We're going to go as far away as the player as we possibly can by going to one of the corners of that square that we defined by setting those 4 Pokemon earlier. So yeah, that's going to be our new current destination. And as we have done earlier, we want to run this little code behind here. Again, don't make the mistake of just calculating this every frame. You just want to calculate it once with the transition key, because otherwise you're doing it too often. And we also want to update our Pokemon animator, and we are going to set our animator this time to, what is it again? So Saunter is going to be false, Flee is going to be true, and this one is going to be false as well. So yeah, that's all pretty neat. I think one thing that I would like to do as well is to make sure that we set the run speed a little bit higher. So let's get in here. And actually, we can do that up here as well. Like, we don't have to call it every single time. So let's do speed equals to, I think we made a variable earlier. Yep, called run speed. So that is going to be lovely. We can do that right there. And yeah, I think we can just do this for now. The only other thing that we want to do is make sure that in our saunters and in our other that we keep the walking speed to where we want it to be, especially with the Saunter. With the chill, it's not that important, I guess. But when we go to Saunter, we want to set our walking speed or our speed back to walking speed. And I don't think we actually have to set it up here for chill, because the speed is going to be, you know, we're not going to be moving because of this anyways. We could set it to 0 if we wanted it to. Why not? Let's set it to 0. 0F. There we go. So we're standing still here. We are walking speed here, and here we're going to be running. All right, so let's see if all that works. Or rather, let's set a semicolon here and see if all of that works. And let's give PsyDuck some run speed as well, because if we put this at 0, obviously nothing's going to work. So then we can press play and see if everything is working the way we intended. So, all right, PsyDuck is chilling. I'm going to wait for PsyDuck to saunter. There we go. So you can see that PsyDuck is sauntering quite some distance. So let's get in between the distance. There we go. Holy cow. Look at him go. PsyDuck, come back. So is this a safe spot here? Did we get this 140-40? Yep. So this is PsyDuck's safe spot. So as you can see, PsyDuck reached it safely. Wonderful. All right. Let's get back to the code and add some more. Or wait, before we do that, I don't want to make that mistake. Let's click on PsyDuck here and make sure that the default run speed is also set for the prefab, so that we don't just end up with, you know, this PsyDuck works and the other one's is going to run into issues. So our prefab, in the prefab, that's where we want to set it as well. But yeah, so then we can get back to the code and continue working on what happens when PsyDuck flees. So here we go. So we want to look for if PsyDuck has reached the destination and the player is not near. So reaching the destination would be similar to what we did for Saunter, and then check if the player isn't too close. And if that's the case, we can go to chill. However, if we reach the destination and the player is still too close, or a certain amount of seconds have passed, just in case our pathfinding gets stuck on something and the player is still too close, we want the dig and have PsyDuck leaves the map. So we're going to implement that part now. Now, both of those states kind of start with a similar condition. So I'm just going to write a method for that, because I think we're going to be using it a couple of times. And it's going to be a void called check for dig. And whenever we call this method, we're pretty much just going to check that distance between PsyDuck and the player using the magnitude again. So transform position minus, trainer dot transform dot position dot the magnitude. And if that is, let's say, larger than 25 meters, like I want the player to just not pursue PsyDuck when PsyDuck is fleeing at all. So let's make it really easy to have a PsyDuck leave the map because you followed them. So here we go. Else we are going to go back to chill. Or, well, actually, no, we're going to go, wait, I'm confused now. So if we are transforming, we are going to go to the chill state, not the flee state. There we go. Right. So at that point we can chill, and in that one we can dig, and that should work just fine. All right. So where's my flee state? Let's implement that here. So first let's start with doing an invoke again. So in this case, we're going to invoke, check for dig, and let's give the player 10 seconds to get the heck away from our PsyDuck. So yeah, that gives us 10 seconds to get 25 meters in between the player and PsyDuck. I think that's reasonable. Because otherwise, if, 10 seconds later, this is going to trigger, and if the distance isn't big enough, we're going to dig, and dig means that PsyDuck is no longer on the map and we lose one of our Pokemon. However, I also want to make sure that if for some reason we end up getting there earlier, that we are also going to check for it. So let's see if, I see I have a problem here because a problem popped up here. So let's see, void is not assignable to type string. Yep. So our method name needs to be a string, not the return of check for dig. So I wrote a little mistake there. So anyways, so if we are getting to that destination, so if transform position minus, there's a current destination, I guess, current destination, if that is smaller than 2.5 feet, so, kind of what we did last time with the Saunter, then cancel that invoke. We're already there, so we don't need to check for dig. And I mean, this is just, I'm not going to super, test this super hard, but this is just some fail safes that my brain is thinking of. So we can just cancel the invoke, and we're going to check for dig anyways. So we're canceling the invoke so that, let's say we get to the destination in 5 seconds, right? We want to check for dig, so that's what this is for. And then we're going to cancel the invoke so that we don't check for dig, it's in the clear, and then we check for dig again when it's not in the clear because we're sneaking up on PsyDuck and he'll get away from us anyway. Like, that would suck. It's fun behavior, but it's a bug, not a feature. All right. So, yeah, so I think that's something that we can do for flee. Now, we're not going to know when we're digging, so we can't really test that much yet, but that's an easy fix. So when we get to dig, we do current destination equals to transform the position. So we're not going anywhere anymore. We might even set the speed if we wanted it to. Like, it doesn't matter at all, probably, because we just did the first thing. I mean, either of these things would suffice, honestly, but I'm going to put it in there anyways for now. All right, and looks like a mistake was made here. If is smaller than, so there's a vector 3 coming in here. So yeah, that's not what we want. What am I doing wrong here again? Oh yeah, the magnitude. Obviously the magnitude. Yeah, this is just a vector that we have as output. Yeah, I've recorded a lot of videos today. I'm getting a little tired. So if you are feeling that you're making a lot of bugs coding, the solution oftentimes is to go sleep. Like I should probably do by now. But we're getting towards the end of this. So, all right. So what was I doing down here again? So I wanted to update my animator. Oops. Update Pokemon animator. And our animator is going to be Saunter false, flee false, dig. Dig is true. All right, so that should have all of that stuff happen pretty neatly. Yeah, now the question is, am I actually going to manage to trigger this? Because if PsyDuck is going to run, yeah, all I have to do is just stay on PsyDuck's tail. All right, let's try this out and make sure that PsyDuck is selected up here so we can follow along and see when it goes to dig. All right, let's press play. Make sure I don't hit him with this Pokeball, and let's get in front of him. Alright, I'm going to 140-40. He's in flee mode. Yep, went to dig. So yeah, you can see you have to get away from him. So that worked fine. let's try the other one now. I'll make sure it works for you as well. By the way, that little floating animation that we have, I think if you extend the raycast, that should fix it. But anyways, let's have PsyDuck run away, and now we go the other direction. Hopefully PsyDuck will go back to chill. Yeah, PsyDuck went back to chill in the current state, so follow along up here. All right, so it looks like all that code seems to be working. So next up, what do we do? Because we've got most of this stuff working. Kind of need to think about what other things that could happen that could go wrong. Like, say, what happens if PsyDuck gets caught in a Pokeball, right? So we need some code for a Pokeball. Yeah, let's look into that. So when we do the code for the Pokeball with PsyDuck, I believe that, yeah, we set the Pokemon to inactive. Okay, let's work with that. So where's my Pokemon controller? Here it is. Where would be a good spot to put this? I mean, the state machine's right up there, so I'm going to put this in between the switches and the check to dig. So it really doesn't matter where you put this, obviously. It's just what I feel makes the most sense to debug the code later on. So private void, and it's going to be an on-disable. There we go. And on disable, we're going to cancel all the invokes, so nothing weird can happen with that. So no switch to Saunter. And that's how the bug happened. Okay, so I guess Ryder doesn't do a great job of that, but whatever. We're going to cancel the check for Dick as well. So if these don't exist, there's no bugs, there's no issues. It's just, well, they'll see like this one exists. And then we are going to switch state to flee. Oh, shoot. State flee. So on disable, so this is basically when we get disabled, we're gonna cancel whatever invokes that we have. So that means we can't start running or digging or whatever. And we're gonna switch our state to flee so that when we get out of our Pokeball, that we are really gonna start running. As soon as that happens. So that's kind of cool. And I think, let's see, when we disable, I mean, we don't have to, because I was thinking maybe I need to add some code to stop moving or something like that, but that doesn't really matter because as soon as you go inactive, and I tried this out, nothing happens anymore. So the pathfinding AI will just shut down entirely and you won't move anywhere. It's just having this type of stuff still on can lead to issues when you get out of the Pokeball. So even though this says on disable, it's kind of what happens when you go active again. But like, I mean, this will work. Let's just put it to on disable. So now our Pokeball should work again as well. So then the final thing that we want to do here as well is when our dig has been completed, we want to destroy our Pokemon so that it's no longer there, or set it to inactive if you will as well. I mean, I guess that would be fine too. But in this case, I think we've been destroying Pokemon when they actually got taken off the map. So let's verify that really quickly by looking at the Pokeball. And let's see in the end. Yeah, we destroyed a Pokemon. So we want to destroy because we can then use that for our level manager when we keep count of how many Pokemon there still are. We can just do a quick query on that. So what I'm going to do to accommodate that is I want to grab the animation event, or rather the animation for falling flat, and add an animation event to it. So double click it so we can get the dope sheet. And we've done this before. You should know how this works by now. But if you haven't, you're going to see it in action one more time. So go to the final frame up here, add animation event. And then with that selected, you can give it a name. And we can call it like, I don't know, dig completed or something. Dig completed. And let's get rid of this. All right. And then back to the code. And all we have to do for that to happen, let's put it here, is to do a public void, because it needs to be public, I think. So dig completed. If it's not public, I don't think the animation event can find it. And then we can just destroy our game object. There we go. And yeah, I think that should be all the code that we need for this specific video. I think this should do almost everything that we wanted. So it should take care when we dig to make PsyDuck disappear as well. So I'm going to run this to make sure I don't have any errors in the script. And you're welcome to follow along with me. So let's see, I'm going to make sure that PsyDuck is selected. So if you're debugging your own stuff, you can see there as well. So if PsyDuck runs into that ball, he's going to get captured. Okay, we got lucky there. So PsyDuck is sauntering, and you can see the location that PsyDuck's going to. And I'm just going to get in front of PsyDuck, and that will make PsyDuck run away and make sure there's enough distance for now so that PsyDuck will go from flee to chill. Still in flee, PsyDuck's back to chill. Now I know, oh, I can see him from here. All right, I'm going to get back to him. Going to let him do it one more time. I feel like this is not the furthest, like maybe I wrote that code not that well. Like I feel like there's a further point on the map that PsyDuck could have run to flee. So that might be something worth revisiting. But like any point will do, honestly. Yeah, no, that's not the furthest point whatsoever. So there is something with the math there that I need to look into. But yeah, and PsyDuck deleted himself, as you can see. So yeah, feel free to update the code to see what the error is there. We'll have a quick look at that as well. And yep, that looks pretty straightforward. This needs to be greater than, and this needs to be greater than. I'm sending PsyDuck into the wrong direction, but that was quite convenient for debugging purposes. So let's see if this works now. All right, so here we are. Let's get in PsyDuck's way. PsyDuck, hello. Don't run onto the okay. Okay, yep, and now PsyDuck is going to the very different direction. Wonderful. So the final test that I want to do at this point, there might still be a bug or something in there. Who knows? Like it could also be pathfinding issues, but let's try to hit him with a Pokeball and see if that causes any issues. I missed. Oh no. Well, at least he's not super fast. Okay. Yep. Lovely. And PsyDuck comes out and he's just sprinting straight away as soon as the pathfinding is completed. So yeah, looks great. Wonderful. Okay, and with that, we are getting to the end of this video.
No? What do you mean, no?
Well, I mean, it's too many bugs, man. You gotta
Get back here!
Oh, Tiny Bob can be so annoying, but he's absolutely right, because there is a bit of an annoying bug in the game still. And actually, it is this specific method that we have here that we are using to calculate our valid destination. Can you figure out what's going on here? So if you saw that we are doing something here with the destination, and then we are adjusting the x and the z, basically voiding whatever we have calculated here, you'd be right. So we're setting up an x and a z, and then we calculate the y value for it, and then we change the x and the z so that, yeah, the y value is no longer going to match up anymore. So what we're doing with our avoid trainer script here actually needs to happen up here. But if we do that, we want to get rid of the destinations, because this vector does not exist yet. So let's get rid of that. And then, so we're setting the x and the z, and then this thing should work just fine at this point, I think. So yeah, that would be a solution for PsyDuck getting stuck. And with that, we actually get to the end of the video. I hope you enjoyed it, and I'm